Robotics, Windows, something, rockets, Keith Packard.
Yay! Okay, well, the bad news is I don't have any movies now. The good news is that at least it's on the screen. Okay, my name is Keith Packard. I'm a principal engineer at Sci5. We make RISC-V processors. I put my email and Twitter handles so that other people could learn them. I'm going to talk to you about some work that I started last December, building a little baby version of Python. It's been awesome for the last 2 days. We've had at least 3 presentations on Python internals, and now you're going to get another presentation that has some things on how you might implement Python a little differently. First, I want to motivate the work, which is going to be pretty hard because it's pretty hard to motivate why you would do another Python implementation, but I'll give it a try. For the last 15 years, I've been teaching a programming and robotics class to middle school students. Middle school students are typically from ages 10 to 12. The class is very small. There's usually 10 to 12 students and 2 teachers and several TAs. So it is a very unique environment, not easily replicatable. We have TAs, which are former students who are now 16 to 18 years old, typically. And we are teaching the program in 3 different languages. We actually teach the students how to build robots out of Lego and how to program the robots in 3 different languages simultaneously. This gives the students exposure to 3 different kinds of programming environments because the students have different educational and learning styles. And so this kind of tries to find a learning style for each student and lets the students choose which environment that they want to build robots in for the rest of the year. So we have Logo on a Macintosh. This is an old version of Logo that runs on macOS version 8, I believe. Yeah. So as I said, I've been doing this for 15 years. I came into the program fairly late. This program started in the mid-90s, I believe. And actually, I'll show you in a few slides, I'll show you the first computer that I was instructed to teach using. And we also use a program called Robolab, which is a blocks-based language that uses the slightly newer RCX bricks, not the more modern Mindstorm stuff, but something like that. One of the key and interesting aspects of this educational environment is the teacher is extremely focused on a cooperative and collaborative environment. How many of you have heard of things like First Lego Robotics or First Robotics League or some of those other robotics teaching systems? I actually volunteer in an all-girls high school in Portland helping with a program like that. And I have to say the competitive aspects of that program are not positive from my experience. Especially when teaching girls, the competitive aspects really get in the way. And oftentimes are a barrier to their participation in a lot of environments. So I'm not a big fan of competitive environments, and the fact that this program is entirely collaborative and cooperative is a huge positive. If you have an opportunity to do a robotics instruction in your life, if you can find a way to make it more collaborative, that almost always has been really beneficial when I've seen it. So that's kind of interesting. When I arrived to teach robotics in the Lego program some 15 years ago, this was the tools that I was given. These are not my tools. My tools burned in a fire of their own making and are no longer operational. One day it's like, Jane, I have bad news and good news. The good news is we get to experience a different computing environment. The bad news is it's because the Apple II is on fire. So this Apple II is an extremely old system. The plug-in box that Lego made, I really have no idea when it was produced. It was certainly not produced after 1990. It was probably produced in the 1970s. But it has a plug-in card that plugs into the Apple II and a little controller box. It has some inputs and some outputs. It's functionally no different than an Arduino, right? It's got the same level of processor. It's got the same I/O capabilities. One of the interesting aspects, though, was you programmed it directly on the device. It has an IDE on the device, and you programmed it in a tremendous language called Logo. Has anybody heard of Logo? Awesome. And Lego, so many Lego. The main instructor for this program actually has so many Lego that she has, I believe, 4 storage units If anybody knows what a United States storage unit, it's basically a cargo container full of Lego that are not being used currently in the program, unlike the Legos we are using. This is what logo code looks like. It's kind of Lisp without parentheses. It's a very, very brief syntax. It doesn't have a lot of structure to it. You can create lists with square brackets, and the forever operator actually takes a list of lists to execute, and it executes these in an infinite loop. The interesting thing about this environment is that the functions to manipulate the I/O devices either take one or no arguments. So when the student has to ask you what order do the arguments go to this function, there's only one order. You either don't give it an argument or you give it one argument. So that makes it actually really easy to tell the students the sequence of operations in a sentence. You don't spend a lot of time explaining, oh, you have to put the port that you're talking to and then the value that you want to talk to after that, or the amount of time that you want to delay, or what order do things go in. So it's actually, you spend more time typing, maybe, but you spend a lot less time explaining, and that actually turns out to be a pretty good thing. One of the interesting things about this particular environment is that the values were all integers. It didn't support floating point numbers at all, and that the times presented here are actually in tenths of a second. And it was interesting for me because it was always that pause in the beginning of the instruction cycle. Now I have to explain what a tenth of a second is. And for most 10-year-olds, they're starting to get fractions. They're starting to understand that there are numbers other than the counting numbers. But to have to pause the instruction in programming and start going into a discussion, oh, these aren't seconds, these are tenths of a second. You have to take the number of seconds that you want and multiply by 10. So it's an additional pause in the instruction, and it usually went okay. But I noticed this more when I moved on to our next environment, which was this environment. After the Legos caught fire and burned, I had to switch programming environments, and I switched to a system called I switched to a system based on Arduino. I had Arduinos and a bunch of plug-in boards. Eventually, I made my own custom Arduinos because I was tired of the stack of boards that we would have with input cards and output cards and batteries. But it was still the 8-bit Atmega 328P processor. This is what Arduino code looks like. I'm sure you've seen this. I'm sure you can't read it on the screen at all. It's C++. Who here is a big fan of teaching young children C++? Yeah. Well, as you can imagine, that went over great with the kids. Some of them could pick it up. Some of them learned enough between the ages of 10 to 12. But by the time they went into the program and became the TAs at 16 to 18-year-olds, they finally started to figure it out. So in 3 or 4 cases, it was successful. I managed to teach children how to program in C, and they finally figured it out enough to do it on their own about 6 years later, which was okay. I felt it's not terrible. At least they're kind of learning it. But I started listening with my instructor ear to what the students were telling me about their learning experience. And C is just a terrible language for students that have minimum typing skills. And at 10 years old, they've been typing for 4 years, which is pretty aggressive. And even still, they don't know what a semicolon key is. They have no idea what a curly brace is. The notion of having the indentation be insignificant was a mystery to them. It's like, I indented it, why doesn't it know? It's like, I'm sorry, C doesn't have syntactic indentation. Oh, and they would get confused by that. So C was an interesting experiment. We built some tremendous robots. I wish I could show you a movie of this running. This actually shows a simulation of fireworks on this display. It's 160 individual LEDs that puts out an enormous amount of light. My camera was very unhappy filming this. It's some more custom hardware with serial connected LED drivers, and you could bit bang every single LED and PWM them fast enough to get them to fade in and out individually, all with an Arduino Atmega 328 processor. C is amazingly fast, and we need to remember that because sometimes that's the tool you need to use. But even the high school students had no idea how this worked. I built this thing and showed it to them and expected, at least one or two of them to figure out. They just looked at the code and were like, "You did what?" So yeah. Okay, so even though C is awesome and you can do some amazing things, I never got the students to learn it. Okay, so C was not such a great idea. I needed to come and have a new plan. I really liked the notion of teaching a mainstream language, skills that the students were going to be able to take out of middle school into high school to do science projects and their own experiments with, and on it in the university where they actually might get teaching assistantships or research fellowships programming. So I really wanted to use a language that was scalable. I really wanted a language that I could teach to 10-year-olds responsibly. I wanted a language that had kind of the syntactic and semantic content of BASIC, which is a language we used to teach to 10-year-olds back in the 70s and 80s. The problem with BASIC is that it's a dead language, and so you wouldn't teach that to even your dog these days. I wanted it to be at that scale. I wanted it to be syntactically simple. I wanted to be able to run it on existing Arduino hardware, and I wanted it to be a really, really small language. C is small, but not quite small enough syntactically. It's small semantically. Okay, so I decided, well, fine. What I really want to do is teach them Python, but my Arduino hardware can't run Python. It's not big enough. And more importantly, Python is a big language. Python is big like Java. Python has a lot of interesting breadth, a tremendous amount of syntax and semantics. It's got object-oriented systems. It's got coroutines that we just learned about. It's a very sophisticated programming environment. I didn't want to teach them all of Python. I could teach them a small subset of Python. I wanted it to be able to run on small robots that drove Legos. And so I wanted it to be something that I could feel comfortable teaching in a few hours. They were going to be able to explore most of the language. I wanted the IDE to run on a desktop like we had with Arduino. I wanted to be able to have robots that were independent and battery operated. With our other two robotic systems, they're kind of chained to the desktop, and that's not a lot of fun. And so I actually came up with a new little programming language that I called Snek. It's a little baby Python, right? Actually, my daughter suggested the name. I suggested, I'm building this new language. It's a small creature. I called it a newt. It's an amphibian, not a reptile, but even still, small, cute little creature. And she said, no, Dad, there's a meme that you need to know about. It's like, oh, why do I have children? Yeah, they teach me things. And so she suggested the name Snek, and I thought, well, that's kind of cute. What the heck? I assume all of you, unlike me, had heard the meme Snek before I started this project. Yeah, this was my first introduction. I think I'm kind of up on internet stuff, and yet my daughter and son continually remind me that I have no clue. So one of the projects that we write is a little line bug, and I actually have one here. And this is the whole program that this line bug does. And maybe I can actually run it on the side of this carpet. Okay, yeah, as you can see, it's got a little computer. It's got two motors and a little light sensor. And so the students are instructed on how to experiment with a light sensor. And this is one place where Python or Snek, anything with a REPL, is tremendously valuable, because they can just use the REPL to talk to the light sensor and ask what the value is. If we have time for demos, I'll try to demonstrate this in a while. But a student built this last week. The instructor said, you are going to get that back to us, right? We need that for class next Wednesday. And so we'll show that in a minute. And as you can see, does that look like Python? Yeah, pretty much. It's got some functions that you've never seen before, but it definitely looks like Python. And you can kind of understand what it does, right? I've been told this is called bang bang robotics, where you turn the motor full on or the motor full off, depending upon the sensor values. It's kind of fun to watch drive around. We'll do that. Okay, so I looked around as I was thinking about what I wanted to build, and I looked around for existing projects, and I looked at CircuitPython and MicroPython. Both of these are much bigger languages. These encompass essentially all of Python in their current implementations. They're much larger. CircuitPython essentially fills the entire flash space on the chips that it runs on, 256 kilobytes. So there's not really any space to do anything else on them. It uses a lot of RAM, and so they don't really have a lot of extra space on them. It's kind of it fits in these chips, but just barely. The main issue that I wanted to get away from with CircuitPython was the syntax they use for manipulating GPIOs. Here's a GPIO program that just blinks an LED, right? Okay, so you have 8 lines, and the only thing those 8 lines do is configure the system to use the GPIO pins. And so if I'm instructing middle school students, it's like, okay, you're going to take these 8 lines and just trust me and type them in, and it will help, and it will do nothing. So from an instruction point of view, it takes about 10 minutes to get the student to type this in, which is basically a waste of time, because you could provide this. And then the rest of the loop is pretty straightforward, except that it's using object-oriented concepts, right? The LED is an object, and instead of calling a function or executing something or talking to something, you actually set a property on an object, and that implicitly invokes behavior. From our object-oriented world, that makes a lot of sense. You're essentially telling an object something. But it's actually a fairly sophisticated concept to get the students to understand, especially when the parallel programming systems that I'm using don't use object-oriented notions at all. And so trying to get the parallel education going between this and the logo environment that we use is fairly difficult. The same code in Snek is a little smaller. It takes a lot less time to type in, and the student gets a positive feedback. It would be, and maybe one of the options that I have going forward is to throw away my Python implementation and just put a library on top of CircuitPython that does all the stuff that I need. And I may explore that, but I've had too much fun. Okay. When I was developing Snek, I needed a code editor. I wrote one in curses, and I'll show that to you in a minute. But then I discovered that there was this existing educational editor for Python called Mu. We've seen examples of it here earlier. I was kind of blown away by how cool it is. So if any of you are learning Python or teaching people how to program in Python, this is fantastic. It's a great project. I've submitted patches to it. They haven't accepted all of them yet, but you know, we're working on that part. It supports MicroPython devices. It supports all the Adafruit CircuitPython devices. You just plug in a device, Mu comes up, and Mu knows all about the Python that runs on your device. I have a merge request pending for the Snek support for this. So if they take this merge request, you'll be able to plug in a device running Snek, and you get all the Snek language support built into this editor. So when you edit code with Mu, it looks like Mu, and it's got the code in it. One of the nice things about Mu is it has the REPL down at the bottom, so you can just mouse down to the bottom, click, and start REPLing to your heart's content. I'm not going to get too much of my internals of Snek, am I? This is the editor that I wrote. It's functionally the same, and I was kind of terrified that they were functionally the same, but it's all curses-based. So then I had to get the kids to figure out how to hit function keys. And on many laptops, hitting function keys involves hitting the function key and then the function key. Yeah, that wasn't so great. The mouse turns out to be useful. Okay, I'm going to spend about 5 or 6 minutes talking about the implementation of Snek, because I spent too much time earlier, which is what I always do, and I apologize. Okay, in my world, I've implemented a lot of different programming languages. It's kind of a hobby of mine. It's how I learn programming languages. I learned C by writing a C compiler. I learned Lisp by writing a Lisp interpreter. I learned Python by writing a Python interpreter. Yeah, maybe it's a bad hobby, but I enjoy it. So I've noticed that there are kind of 3 general classes of languages. There are languages which are directly interpreted. And in my mind, these are things like BASIC and Lisp. And the way that I define these languages, the source code is the executable. There's no separation between what the source code is and the executable. In Lisp, when you type the source code in, it's lexed into a data structure, which is essentially the source code, and that data structure is directly interpreted by the interpreter. In BASIC, the text of your program is carefully walked over by the interpreter during execution. How many of you have programmed in BASIC? Awesome. How many of you remember optimizing your BASIC program by removing the comments? Yeah, literally it would go faster when you remove the comments because it didn't have to carefully step over the comments. Another class at the bottom here are fully compiled languages. These are kind of the first programming languages that we came up with, like C and Fortran. In these, the compiler output runs directly on the CPU, right? You actually compile the code to native assembly code, and it goes zippy fast. And in the middle, we have this newer class of languages called byte-coded languages. So Ruby, Python, Java, the early implementations of Java were all bytecode interpreted. You compile the application to a bytecode, and then you construct a virtual machine that executed the bytecode. And the reason for that is that the virtual machine is usually easier to get a semantic match to your language, so you can put complicated operations into the bytecode that do exactly what the language wants, and then you can spend a bunch of time implementing those in the VM instead of having to figure out how to write a compiler to generate enormous instruction sequences to do stuff. It's also easier to do managed memory in these environments because you have a lot better control of the execution. And it's way easier to write a portable implementation because you only have to write the interpreter for the virtual machine once, and then you can recompile it for whatever your target is. So if you have one of these compiled languages that compiles to your native instruction set, you can implement a new language in that language that executes in a virtual machine. So that's why these bytecoded languages kind of appeared last in our history. We first had compiled languages, then source code interpreted languages, and now we have bytecode interpreted languages, because we really needed solid compiled languages to get there. Snek, I want to talk a little bit about the implementation in 4 pieces. There's a compiler, because it's not really an interpreted language. It's an interpreted virtual machine, but there's a compiler that generates the virtual instruction set. There is the virtual machine that actually executes the bytecodes, and we've seen a lot of examples of bytecodes being executed on virtual machines this weekend, which is fantastic. And then underlying that, there's hardware support. How do you talk to the underlying processor? How do you talk to the underlying pins and get the outputs to actually wiggle? All of the Snek implementations that I've done so far run native on the metal. They're bare metal Snek implementations. So there's no operating system. There's nothing. There's code that talks to bits. So they're very, very low level. And there's a memory manager, which is kind of a cool thing. Snek has a few data types. It has 32-bit floats. It does not have integers. How many of you have worked in a language with no integers? Yeah. JavaScript? Basic? Yeah, Basic didn't have integers. It has one data type that I use to represent all of the kind of basic collective types in Python, tuples, lists, and dictionaries. I have strings, and then I have compiled functions, the byte-coded functions, and then I have built-in functions. Then I have a couple of constant values. Okay. I wanted to be able to use 32-bit floats. I didn't want to have to allocate memory for 32-bit floats, because that's ridiculously expensive and churns through memory at a prodigious rate. So here's the hack. This is the best part of Snek, I think. Okay, if you look at a 32-bit float, it's broken into 3 parts: a sign, a 1-bit sign, an 8-bit exponent, and a 23-bit significand, or a mantissa, as it's sometimes called. It turns out that in the IEEE standard, if the exponent is all ones, then that is not a number. The significand can be any value you want, and it's not a number. That means I actually have an opportunity here. I can encode, using those 23 extra bits, whatever value I want as a nan, and I can tell it apart from other real floating point values. So here's what I did. I set all upper 9 bits, so the sign bit and all 8 bits of the exponent, to 1. Now I have a signaling nan, a so-called signaling nan. Now I use the bottom 23 bits to encode my other values. And I use the bottom 2 bits as a tag bit, which is kind of a traditional thing to do. You put the tags in so you can tell your basic representations. So a string is tag number 2. I think a list is tag number 1. And something else is tag number 0. I don't even remember. But I get, there's 16 million nans. So I'm going to use 8 million of them and kind of ignore the sign bit because it's just too hard to deal with. That means I can easily access 8 megabytes of memory. Oh my God. Yeah. The largest device I have is 16 kilobytes. I think I'll be good for a while. Okay, so now I just pass around floating point values, and I have pointers and whatever I want. I wrote my own parser generator, just like Guido, because I needed the most compressed parse tables I could get. The parse table are 1,200 bytes for almost all of Python syntax. When I did the same parser in Bison, it was about 6,000 lines of code. I am running out of time, and there's lots more to the implementation of Snek. I wanted to mostly motivate you that I wasn't entirely crazy to build this new language. Probably the most important thing that I wanted to tell you today, yeah, see, I have lots more here. Oh, there we go. Was the fact that I have built this customer hardware called the Snek board. And starting in a couple weeks, we're going to start a crowd supply campaign. If you're interested in running Snek or CircuitPython and controlling Lego motors and using Lego input devices, we built custom hardware, and we're actually going to be running a crowd supply campaign. There's the URL. It's live now. You can go see some preliminary information about it. And the crowd supply campaign will be starting in a couple of weeks. And I want to thank you all very much for your time this afternoon, and thank you for welcoming me to your conference this weekend.
Thank you, Keith. Now, I'm one of these